So the idea, again, when we're tackling these kinds of problems is to first identify the critical points and then investigate those critical points using the second derivatives test. We're going to learn another technique, something called Lagrange multipliers, that'll help us, I was going to say, in a more efficient way. That's not always true. Sometimes it's more efficient, but sometimes it isn't. Oh, you know what? Before we get to number 3, I see that I have a note here that says try this, case 3. All right, and so it looks like we didn't finish number 2. So let's tackle that one. So I can get rid of this notation. So we discovered the location of the local max, or at least what appeared to be the local max. We discovered location of saddle points. The one thing that we didn't get out of this was the local mins. All right, and so what we did was we chose X values that corresponded to the 2 different sets. So first I chose an X value from the first set, the sine functions, and then an X value from the cosine functions, and paired that with the corresponding value for Y. Right? Because we need to have mixing and matching of different values, it kind of makes sense that that would be the case. All right. Now, what we end up with is a little bit of an issue because we're out of possibilities, but we haven't addressed the minimum yet. So one thing that we could do is go back and revisit some of the cases that we've already tackled and just kind of move a little bit further down the line. So for example, looking at what we did in case 1, we took, that's the yellow highlight. So we took 0 and pi over 2. What if, for example, we took pi and something from the set of pi over 2, 3 pi over 2, 5 pi over 2, and so on. So maybe we still stay with the pi over 2 for consistency, or maybe we jump down to 3 pi over 2. It kind of makes sense that we would go a little bit further down the line just to see what's going on there. All right. So x, we're going to try x is equal to pi, and y would be equal to 3 pi over 2. All right. We still have to go down the list by substituting these values into the first, or the original function, so f. The second order partials all around, so f sub xx, f sub xy, well, I'll do yy just to keep it consistent, and then f sub xy or yx, because they're continuous, it wouldn't matter which one we go with. All right. Then from there, we would need our discriminant, which is going to be based off of whatever we turn up with here. All right, so let's investigate by popping these values, the pi and 3 pi over 2, into the original function. Cosine of pi is going to be equal to a -1. Sine of 3 pi over 2 is going to be equal to also -1. So we get a 1, right? So really no help there. But what we could do is kind of go back. My original suspicion was hang on to this guy. Instead of going to 3 pi over 2, maybe just hang on to, or just go on to a pi. And the reason why I say that is because we would actually get a -1 if this is just a pi over 2. Right, because as we saw here, cosine of pi gives you the -1. If this were positive, then we'd get a negative result. Right, so that's what we want to do. We want to kind of manufacture it so that that would be positive. So the only way that this would happen, or one of the ways in which this would happen, is if we worked with a pi over 2. All right, so my initial suspicion was incorrect, but it kind of led me down a road that got me to a more appropriate pairing of values. So pi over 2 corresponds to a -1. We know that that's going to be a minimum value because it's symmetrical, and we established that the maximum value was 1. So that would give us a minimum of -1, right? So we plug these values into our second order partial with respect to x, right? So I'll use the blue highlighter. So that's x and y, x and y, but pi and pi over 2 going in here, right? If you replace a sine with a pi over 2, that's going to give me a 1, negated as a -1, but then the cosine of pi is also going to give me a -1, so I'm looking at a +1. So -1 times -1 would give me a +1. All right, do the same thing. This time y. Cosine of x, -1. So cosine of pi, -1. Negated is +1. Multiplied by 1 is going to give me another 1. All right, and then f sub xy, sine of x, sine of pi is going to be 0. Doesn't matter what everything else is, it's going to be just a 0. So for D, I'm looking for the product. So 1 times 1 minus 0 squared is going to give me a result of 1. All right. So we look at our relationships here to see what the story is. If D ends up being a positive number, then we could be looking at a relative max or a local max, or it could be a local min, all depending on what f sub xx is. F sub xx in this case is positive, so that means that we're dealing with a local min, right? So specifically, in this case, we're looking at a local min at pi over 2, -1. All right. So what we want to do is consider under what circumstances we would get extreme values of 1 followed by -1. So we have we had the initial claim that the extrema would happen, or I'm sorry, the maximum values would happen at pi k and 2k plus 1 over 2 pi. But it seems like that was kind of like an overstatement because that didn't account for the local min, right? So we want to account for that also. So it seems like if we're alternating, so 0, 2 pi, 4 pi, 6 pi, and so on, that would, if we go with pi over 2, that seems to get the job done, all right? But then the big question would be, well, what would happen if it's not pi over 2? So what we can do is kind of just a quick exploration here, and that could be just a simple matter of making a table of values. All right, so I'm going to get out my Desmos calculator and show you what I'm talking about here. Not OpenStax, Desmos. I'm just going to make a quick table. All right, so I have 0. I got pi, and we'll just focus on the positive ones for now. 2 pi, 3 pi, and so on. All right. Now, if I match those up with the corresponding values of y, now there's no indication that it needs to be a 1-for-1 kind of deal, but we got to start somewhere, so that's where we'll start. Oh, that's not where I wanted to write it. Pi over 2. It's jumping on me. 3 pi over 2. 5 pi over 2. 7 pi over 2, and so on. What I could do is I could just pop in my relation here and say cosine of x, sine of y. So x1 specifically, cosine x1, sine y1. All right, so it looks like in all of these cases we end up with a +1. So if we do a 1-for-1 pairing, of like 0 with pi over 2, then pi over 2, I'm sorry, and then pi with 3 pi over 2, then 5 pi over 2, then 2 pi with 5 pi over 2. So multiples of pi combined 1 for 1 with those values in y, then it works out just fine. But if we offset the pairings, all right, so let me go back here. Let's see if this is going to work out easily. Yeah, just delete and start off with a pi over 2. I don't know if that's going to easily be done. I think I just have to type it in. You see that the positives all become negatives. All right, so it seems like I get my local minimum values just by offsetting my, well, maybe you don't see it because I didn't really show you, but they're all negatives, all right? So just by offsetting the x value with the corresponding value of y in the second set, it tends to play out the right way, all right? So what we could say here, it's not very different, but it's related to the same information. So I could actually kind of snag a lot of this stuff here. Oh, that jumped. I'm going to kind of move it down and reorganize it a little bit. So this is local min. All right. Now it seems to be pretty much the same relationship, but it's a question of the start value. All right. So what we would have to do is establish that this thing is starting or really only offsetting the value of k and how it relates to the y based off of pi going to pi over 2. All right. So what we can actually do here, it's kind of nifty, is we can establish a relationship between the first and the second value, all right, and then go from there. So if I'm letting the coefficient of pi be whatever I want, it seems as though just by chopping that value in half, we'll be in pretty good shape. So if my next value is 3 pi, then 3 pi over 2 would be the next one. And we can verify that here. Just having a quick look if Desmos lets me do it. Doesn't seem to want to. I can't even get my, no, there we go. Then it disappears. All right, hold on. I guess I got to scroll back. All right, so like 2 pi becomes, corresponds to a 3 pi over 2, which is kind of weird. So it's definitely not that 2-to-1 relationship, but there's definitely something going on here. All right, so if I say pi k, just like we did, but then establish that the next value, the first value has to be a 1, and that we're increasing by odd numbers from, is it odd, actually? Yeah, it's odd numbers from there on out, then we'll be in pretty good shape. So what I can say is that we want to start off with a 2k. That would double the value of k. So 1 becomes 2, but then minus a 1 to get it back down to a 1. Divided by 2 makes it pi over 2, where k belongs to the set of integers. So if k is the number 1, then we have our 1/2 pi. If k is the number 2, then we have the 3 pi over 2. So then we have that consistency that we're looking for, which allows us to generalize our local minimum. All right, so a little bit more doing there in the thinking department, but definitely very, very manageable. But it it does take a little bit of patience. And by a little, I mean a ton. Right? The trig ones are always like that, unfortunately. I guess not always. There's no such thing as always, I guess, when it comes to this stuff. I'm just looking for my chapstick. Yeah, there it is. But they usually have a lot more going on with them, right? So you just got to be careful. All right. Number 3, back to the polynomial-based type relations. So we have f of x comma y is equal to y squared minus x squared. So we get our first order partial. I'm just going to kind of pop it in here. Negative 2x, positive 2y. F sub xx, negative 2. F sub yy, positive 2. F sub xy is just going to be a 0. So that's not bad in terms of computations. Definitely a whole lot easier than what we just did, right? So there's not going to be any cases here. It's just going to be just jump right aboard and see what's going on, all right? So we're going to set our first order partials equal to 0. So x equals 0 and y equals 0. So if there's going to be an extreme value, it's going to happen at the critical point of 0, 0, and then f of 0, 0. Well, actually, that's easy enough to compute, right? F of 0, 0 is going to be 0. So it's going to happen at the origin. All right, so now we just have to verify that that's the case. All right, so f sub xx, f sub xy, f, oh, no, I like the yy first. F sub xy, and then d. All right, so 0, negative 2, positive 2, 0, and then the products. So negative 2 times 2 minus 0 squared is going to be a negative 2. All right. So we're looking at a negative d value. Negative d values. Oh, well, I kind of shoved this down here, but then I never resized it. The only thing that you never want to see happen when it comes to the second derivative test is you never want it to be a 0. You never want to get the d value to be a 0, because that means that you just wasted your time. If the d value is anything other than 0, then you've drawn a meaningful conclusion. In this case, we have a saddle point because it's negative. At 0, 0, 0. Now, this is actually the graph of a saddle. So if you really look at it, you see those parabolic relationships, like it takes on the shape of a saddle, right? So that's kind of what we're using as our exemplar situation. All right, so moving right along, the next page. We have shortest distance. This is a fun problem. Shortest distance from the point 1, 0, negative 2 to the plane x plus 2y plus z equals 4. Okay. So what we're going to do is establish distance in the three-dimensional plane. We know is the difference between the x value squared plus the difference between the y value squared plus the difference between the z value squared. Okay. So what we're going to do is write a relation that shows the distance from this point to any point along that plane. All right. So what I can say is, again, by definition, and I'll just write out the model just so you have it. We're talking x minus x sub o squared plus different variations of it, but this is the most useful one. Z minus z sub o. Difference between corresponding values of x, y, and z. The benefit of writing it this way is that it keeps one of those dimensions variable. All right. So what I would say here is that I have x sub o, y sub o, and then z sub o. So this would be the square root of x minus 1 squared plus y minus 0 squared, so y squared, plus z minus negative 2, so z plus 2 squared. So that's our distance, which we can call f of whatever, f of x comma y. Problem is, it's a function of 3 variables. If we have a choice in the matter, we'd like to avoid having 3 variables. We'd like to get it down to 1 variable if we could, but we can't. All right. What we have here, though, is a relation x plus 2y plus z is equal to 4. All right. So we have z equal to 4 minus x minus 2y. So that's going to allow us to swap out the z for another expression. All right. And then from there, we have the ability to differentiate. The issue is, among other things, it's pretty complicated. All right. So let me rewrite and I'll show you. And by the way, it was a non-starter in this problem unless we had a way of swapping out the z, because otherwise we would have a general relationship comparing a point to any plane, right? Not a specific plane, but any plane in general. And that's not what the question's asking. So we would have had to kind of go back to square one on that. All right. So this is what we're up against here. Let me get rid of this. So this is what we have to differentiate, right? So that's our distance, which I'm going to call S for distance. We try to stay away from D because we're about to use D a lot. Well, depending on the notation that you use to represent derivative. All right. So we would have some pretty crazy chain rule here, except what we could do instead is say S squared is equal to all of this stuff. And define S squared as our function of xy. The reason why we're allowed to do that is really the size relationship between a distance and a distance squared. Yeah. If we're looking to find the shortest distance, we're looking to minimize distance. Minimize meaning, again, the extreme value, but on the low side. If I could find the lowest or the smallest squared distance, that's going to be compared to other squared distances, right? It would still be a minimum. And so once I figure out what the smallest squared distance is, then I would just have to square root that, and I'll know what the smallest distance is, all right? Because it's basically apples to apples, all right? So it's kind of like standard deviations, if you're familiar with that. You know, if you're looking at a measure of variation, you might compare variances, which is the standard deviation squared, all right? The smaller the variance, the smaller the standard deviation. So if I have 3 data sets, I could find out of the 3 data sets, the one with the smallest variance will also have the smallest standard deviation. So same idea here. the one or the value that is the smallest squared distance will correspond to the smallest distance. All right. So I want to differentiate this, and it's going to be a lot easier because it's less in the way of chain rule. All right. So I'm going to go through the process. It's definitely a beefier function, but it's a lot better than it could be. So we could find f sub x 2 times x minus 1 plus y squared is going away because we're treating that as constant. So 2 times 4 minus, oh, really, we can combine the terms. You know, let me do that really quickly. Right over here. 4 plus 2 will give me a 6. All right, so 6 minus x minus 2y to the first power multiplied by the derivative on the inside. The derivative on the inside is only going to be related to the negative x, which is going to become a negative 1. All right. For the sake of sanity, I'm going to clean this up a little bit because we have to take the second derivative or second order partial. 2x minus 2. All right. So this negative 1 can get multiplied by the 2 to become a negative 2. When distributed, we get negative 12 plus 2x plus 4y. 4 quality x, let me clean that up. So 4x plus 4y minus 14, barring any kind of mistake. All right. So we can get from this f sub xx, which would just be a 4. And we can get from this f sub xy, which would also be a 4. All right. The only thing I'm missing is f sub yy. So I just got to go back to scratch there and get that. So we're working again off of this one. So first term goes away. We'll have a 2y minus 2 times 6 minus x minus 2y times a negative 2. Derivative of the inside is only related to the y. So, oh, apologies. This is f sub y. We're not at the part where we can find yy, as much as I want to. Not quite there yet. All right, so I have a negative 2 multiplied by a negative 2, so that's going to give me a positive 4. Distribute. Combine like terms. We're looking at negative 4x minus 6y plus 24. Now I can get my f sub yy, which is going to be a negative 6. All right, so, you know, a fair amount of heavy lifting here, but it's still not as bad as the trig one, if you're keeping score on that sort of thing. So I got what I need in terms of a function, its derivatives. Now I got to get the particulars. All right, so I need critical values. And then from there, I need to test those critical values. So I have f sub x, which needs to be equal to 0. Same thing with f sub y. Simplified form is a good thing to have in this case. All right, it's a function of 2 variables, which is aggravating, but manageable. Now I'm going to write it as a system. So we're looking at, so these two guys come together to make 4x plus 4y equals 14. And then 4x plus 6y. I'm just adding them, the negative 4x and negative 6y to both sides to give me a 24. Now you can do it any way you want. I'm a big fan of the Desmos matrix calculator, which I don't have up. And this would be a 2 by 3. 4, 4, 14, 4, 6, 24. Reduce row echelon form. Put it in fraction form if you want. And so we get x is equal to negative 3/2 and y is equal to 5. All right, so we have our system that worked out nicely in terms of the actual values. I would have liked whole numbers, but we'll settle for what we have. Now we just have to verify that this is going to give me a relative or a local min. All right, so I need the f at negative 3/2 comma 5. I need f sub xx, f sub xy at those same points, but fortunately this is all constant. All right, and f sub xy. I'm sorry, f sub yy. I keep doing that. Maybe I should just write the f sub xy first, organizationally. This just makes more sense when you want to put it into the discriminant formula. So 4, negative 6, and another 4. So D is going to be equal to negative 24 minus 16 is going to be equal to negative. Is that right? Negative 24 minus 16 is, yeah, negative 40. Well, that's a negative number, which would make it a saddle point, which means I screwed something up. Looking. Didn't even rely on the coordinate work I did there, so I don't even have to look at that. X, Y is 4. It's probably something with basic algebra, usually where I botch it. Or Y. Two Y. Two times 6 minus X minus 2Y to the first times a negative 2. Negative 2 times negative 2 gives you a positive 4. Two minus 8 is negative 6. I am not seeing it for some reason. Because if that were positive, it would all work out. And it's not. I'm just double checking everything now. X minus 1 minus 0. Checking. I'm not seeing it. I'm not seeing what I did. So yeah, because what I did for some reason is I was working off of f sub x instead of f sub xy when I was pulling the coefficient. I don't even know why. So let me just clean this up. So I'm actually gonna, just for the sake of clarity, I'm gonna do the f sub yy part again. So part of it is obvious, 2y, but then plus 2 times, I had a minus there originally, 6 minus x minus 2y to the first power times a negative 2, which is going to give you 2y minus 4 times 6 minus x minus 2y, which distributes to 2y minus 24 plus 4x plus 8y. And then when we combine, we get 4x plus, looks like 10y minus 24, which is not f sub yy. That's just a simplified form. Bless you.
Thank you.
Problem.
Forgot my mic.
You know, it's with remote classes, it's one of the few instances where somebody can sneeze and it's like, hey, I feel like we're back to normal. You can sneeze and we can all say bless you and then everything's fine.
That's true. That's true. Nobody's looking at you like crazy.
Like, what kind of animal are you sneezing? You know, like
Yeah.
the little sense of normalcy. It's refreshing. So f sub yy is going to be equal to a clean, looks like a 10 there. All right. So that's going to change this. And so x, y, y gives you a 40 minus the 16, still minus 16 barring any catastrophic error there, is going to give you 24, which is a positive value. All right. That part you didn't need help with. So we got our positive value combined with a positive first order partial with, actually we don't know that yet. So we also need, because this is telling us that we have an extreme value, it's either a max or min. Now I need to evaluate f sub x at -3/2 comma 5, which, you know, isn't crazy in terms of difficulty, but it still, you know, requires a little bit of work. So 4 times -3/2 plus 4 times 5 minus 14 gives me a 0. Double checking. So that gives a result of 0. don't remember getting either. So, all right, so I'll come back to this in a sec, but when we look at our relationship here, we have if D is greater than 0 and f sub x, oh, dang it, what did I do? I can't get out of my own way now. Just ignore me. Ignore me. I'm just being stupid tonight. F sub x is positive. Dang fool. It's like the snowball effect for me. Once I screw up one thing, you've seen it. You've seen it throughout the semester. Once I screw up one thing, it's like everything else is just the cascading effect afterwards. I don't even know. Can't blame it on Mondays either, because I make the same mistakes on Tuesdays, Wednesdays, whatever. Anyway, so this is telling us that we have a local min. All right, a local min when?
Professor?
Yeah.
Don't you have to change the matrix now? Isn't that 4x plus 10y minus 24? Like when we're finding the matrix? The value is not 6y anymore, right?
Oh, good call. Good call. Yeah, so like I said before about, screwing stuff up. Here we are. So 4x plus 10y. And then minus a 24. Positive 4x. Probably should have just rewrote the whole dang thing. All right, so 4x plus 10y. Yeah. Okay, so now these are going to be more in line with what I actually remember being the correct answer, which is, kind of nice. The other one should be fine. We'll see. R ref A, 11 over 6. Kind of like the other numbers better. 11 over 6, 5/3. Now, fortunately, those values were irrelevant to the second order partials. So that's something. In terms of putting the pieces back together here, it ends up being a little nicer. Right. So then I just need to know what the z value is that goes along with this x and this y. All right. So that's just plugging and chugging away back into my original model. Right. Now, bear in mind, I'm not asked to find a coordinate. I'm asked to find a distance. So once you get your x and y, you could actually evaluate your distance formula. I just dropped my phone onto my ankle. Oh, my phone. So we could write our local min statement like this, but then all we'd have to do is go back to our original function and replace every x with an 11 over 6 and every y with a 5/3. All right. The benefit of using Desmos for that, among other things, is the substitution component. Right. So, oh, that hurt. Caught the corner of the phone right on the pointy part of the ankle. It's freaking killing right now. All right. So I'll pop this into my distance formula. All right. So the square root, and I'm going to use A's and B's instead of X's and Y's, because I want my my distance formula to be variable, but I also don't want it to be a function, because Desmos only understands parametric functions, vector value functions, things like that in a particular way. It doesn't really handle multivariable functions very well. Okay, so I'm just going to type this in using A's and B's. Now you can crunch the numbers easily enough. You don't need to do it this way. I'm just showing you a different way to look at it. All right, so I'll leave it up to you to decide whether this is something that's up your alley. All right, so a minus 2y. Well, actually, I can go back to a 6 there. Minus. And then I'll select all for my sliders. And, oh, I got to define it, S equals. All right, so that's my distance formula. Now what I can do is I can just kind of slide back and forth here and determine values based off of that relationship. And it gives me a function model. And just get the S value down here. If it'll let me. And this should be fine. It usually reports it. Okay, well, I guess not. So that gives, oh, I put a Y in there. Foolish. I was like, why isn't it giving me the number like I would want? Right, now that's better. Right, so now depending on how I slide this around, I'm going to get varying distance values. And you can see some of them are bigger than others. You know, slide the A, slide the B, and we get different values, some larger, some smaller. But then in theory, when I get to 11 over 6, so let me replace this A value with an 11 over 6, and the B value with the 5/3, that should give us the minimum distance. All right, so find the shortest distance from the point. The shortest distance is going to be about 2.0412. So shortest distance. I made that more complicated than it needed to be, and I apologize. I thoroughly apologize, but them's the breaks, I guess. What happens is you go down a rabbit hole and you end up screwing things up, or screw up one thing, screw up another thing, and all of a sudden you find yourself in kind of a pickle. All right, so, but yeah, we got there eventually. It just took probably triple the amount of time than it should have.
So the distance is a minus 1 squared plus b squared plus 6 minus a minus 2b.
Yep.
Okay, because I couldn't see.
And I let the sliders be A and B so that I can get a look and see what the relationship is based on different values for A and B. And you can see that it was kind of every other value seemed to be bigger. And so 2.0412 seems appropriately